Hi, welcome to these M1 revision videos. First question I wanted to have a look at was this one. It says there's three forces, F1, F2 and F3, which I've underlined as vectors, and they act on a particle. The F1 is defined by this set of components of I and J. F2 is this one and F3 is this one. They give us everything except the components P and Q for force number 3. And they say, given that they are in equilibrium, find P and Q. The first thing to realize about, well, obviously the most important thing about this whole question is the fact that they say that it's in equilibrium. But what that means in terms of vectors, it's really interesting when it's three vectors like that in different directions. If we look at it in two directions, then it's a good starting point to think about what's happening. One force on its own could not be in equilibrium, right? You can't have a force which is applied on an object if there's no other forces on it. It's never going to be in equilibrium. It's always going to make it accelerate in that direction according to F is equal to ma, right? So one force cannot be in equilibrium unless it's a zero vector, and then it wouldn't be a force. Or and with two vectors you can now have an equilibrium, right? They have to be in opposite directions, so that when you add them, they would be, for example, 3i and minus 3i, so that when you add them you end up with 0i. In other words, just a magnitude of 0. There's no force acting on that vector, and it's in equilibrium on that particle, sorry. Now if you add them together, what would be your final resultant? If you put them on top of each other, you end up with one point in this way, the other one point in that way, and the overall result is 0. So you start from the tail of the first vector, and you end up on the head of the second vector, and you end up with a 0 vector, and that's why it's in equilibrium. The same thing happens here with three vectors. If you have them like one vector pointing in that direction and the other vector pointing in this direction, then if you add them, what would happen? You'd have to bring, with the parallel rule, you'd have to bring this vector to the head of the other, right? Or the other way around. Doesn't matter which one you bring to which head. But if you start here, and if you want to know what the addition of both vectors is, you imagine that's a straight line, so it's not very good. You'd have to bring it here, this one, and draw it there. And now you have the addition of both vectors. If now you want to add a third vector which makes these guys be in equilibrium, you need to go back to the beginning from the head of the last vector. So the last vector would have to take you back to the 0 point, so that the three vectors together add up to 0, the same as these two add up to 0, and therefore you have a situation with equilibrium. Hopefully that makes sense. So if the question is giving me three vectors which are in equilibrium, then it must be that I have one vector like this, for example, another one like that, and there must be a third one closing the loop and taking me to the beginning again, so that the overall sum is 0. The overall sum of that would be 0. And if you had 10 vectors like this, as long as the last vector points there straight to the point where you started, then the sum of all of those vectors is equal to 0. That idea is a simple one, but it's a very important one to solve this question, because then you know that the addition of these three vectors and their corresponding components are going to have to give you 0 as an answer. So that's your way of solving it. I always draw vectors as column vectors because I think it's much quicker, so instead of drawing all of that, I just say minus 3 on the I component and plus 7 on the J component. So it must be true that this vector in newtons plus this other vector, which is 1 minus 1 for the second one, plus this other one, which we do not know, P and Q, have to equal 0. And that comes out straight from what I was saying right now. So all the components. If it had three components with a K, then you just add a third number down here. You make the brackets longer. Alright, so this is really two equations disguised as one, so we can open it up by saying that this means that minus 3 plus 1 plus P is equal to 0, and 7 minus 1 plus Q is equal to 0. From this we can tell that minus 3 plus 1 is minus 2. Pass it to the other side, so that means that p is equal to 2. And from here we can say that 6 is equal plus q is equal to 0, so q has to be minus 6. Alright, hopefully that makes sense for the first part of the question. You can follow that argument for every time you get that question, that statement that three vectors are in equilibrium. You can add them and they must give 0. Second part of the question says the resultant forces of F1, so the resultant of summing F1 and F2 is equal to a vector R. So it just says it in words, but I'm translating it into maths as I'm reading. It says that the sum of those two vectors gives you a resultant R, and they ask us for the magnitude of R. So let's do that now. We have F1 here and F2, so we can just add them and find the magnitude. And this is an exercise in seeing if we remember how to find the magnitude of a vector. I'm going to write the answers in white, be a bit more consistent. So F1 is minus 3 and 7, the same as the one up there, and F2 is 1 minus 1, and they tell us that that is equal to vector R. So vector R has to be minus 3 plus 1 is minus 2, and 7 minus 1 is 6, so that must be vector R. Ugly sixes. Okay. So the question asks for the magnitude. How do you use the symbol for magnitude in vectors? Well, like that. That's the magnitude of a vector. And how do you find it? You have to do the you have to use Pythagoras. So the idea was that this is my vector, so this is the x coordinate and this is the y coordinate of the vector, the coefficients of the I direction, xi and yj. So how do you find the magnitude of that? Well, it's going to be the coefficient of one plus the coefficient of the other square rooted by Pythagoras, right? So I can use that idea here and say, well, this is my x coordinate, that's my y coordinate, so I can just square those two, square those two and square root the answer. So that's the square root of minus 2 squared, which is just 4, plus 6 squared, which is 36. So that is the same thing as root 40. And root 40 can be reduced further. You can just do it in a calculator if you want, but I like to reduce the search if possible. What is root 40? That's the same thing as root of 4 times 10, which is the same thing as root of 4 times root of 10. And root of 4 is just 2. So that's 2 root 10 would be the way that I like to leave it, because it's an accurate number. What are they called? An exact answer. Sorry, it's not rounded up or down, but you can get your calculator and do it in decimals, and you wouldn't miss marks for expressing that in decimals. Just use one significant figure maximum. Sorry, one decimal place maximum. So part C has the following request. It says, calculate to the nearest degree the angle between the line of action of R and the vector j. So the line of action of R and the vector j. So the R is minus 2 and 6. So we need to find angle between vector R and the direction j. So minus 2 and 6 is the vector. Let's draw it so we have a rough idea of where it's going. We have minus 2, so 2 in that direction, and then I'm going to draw it somewhere else because otherwise it won't fit in. Minus 2 in this direction, and then 6. 1, 2, 1, 2, 3, 4, 5, 6. So it's quite high in that direction. Cannot draw a straight line for my life. Okay, I'll do. And we know that this is 2 and this is 6. Minus 2, 6. That's our vector R that we just computed. And they're asking us for the angle between this vector and the direction j. So let's see. So we want the angle between, this is the direction positive j, we don't want this one negative j, we want that one. And so we want this angle. Do you agree? I hope you don't agree, because this is not direction J. That would be crap. That would be direction I. So that would be doing the question wrong, and I suspect some people would probably make that mistake. It's easy to make, but J is this guy. So they're actually asking us for this tiny angle there. So we should get a small angle, and I suggest the best way to do that is to take this as a rectangle and say, well, this is 2 and this is 6 also, so you can calculate this angle straight away. Alternatively, you can find this one if that's a bit strange, and then do 90 minus that. See that this part of the rectangle is a 2, and that a length of 2, and this would be a length of 6. So then I can just say, well, SOHCAHTOA, this is sine, no, this is tan, opposite over adjacent, 2 over 6. So 2 divided by 6 is the tan of the angle that I'm interested in. So the angle should be tan to the minus 1 of 2 over 6, or 1 over 3. And the angle comes out to be 18.4 degrees for the arrow. Alright, so hopefully that made sense, and I'll go on to the next question in the next video now.